Let's have a look at the graph of y equals tan x. Very different to our sine and cos graphs, which were our wave graphs. This one, as I said, is a totally different shape. Let's have a look at it first of all. Here's the graph of y equals tan x. And if we look at it in detail, we can see that it contains asymptotes. Why does it contain asymptotes? Well, at certain values, certain angles, tan theta is undefined. If we look at our table or we calculate it, we know, for example, that tan pi on 2 is undefined. Hence, when we've got pi on 2 here in our axis, we've got an asymptote. The graph isn't defined at that point. Same at 3 pi on 2, same at neg pi on 2, same as 3 pi on 2. So tan graphs have asymptotes. And they also have that, it's almost like a cubic graph shape to them, where they start up here, obviously near the asymptote, they wind their way down and around like that. So that's the basic shape of the tan graph. They have asymptotes at plus or minus pi on 2, and plus or minus 3 pi on 2, and plus or minus 5 pi on 2, and so on. In fact, you can work out what the vertical asymptotes are by using this little formula here and substituting in values for k. If I put in the value of k equals 0 to start with, okay, I get a asymptote at pi on 2 because 2 times 0 is 0 plus 1 is 1. 1 times pi on 2 is pi on 2. Then if I use k equals 1, I get 3 pi on 2. Because 2 ones 2 plus 1 is 3. 3 times pi on 2 is 3 pi on 2. And so on. So I can use that little formula to find the vertical asymptotes. So the graph passes through 0, 0. That's because the tan of 0 is 0. Another thing to consider here is what is the period. Now, the way we work out the period here is a little bit different to what we did previously. But the period here is the distance between, horizontal distance between asymptotes. So you can see there my distance between those two asymptotes is going to be pi. And in fact, there's a formula for the period of tan graphs. And the formula is period equals pi over n. We'll get back to that in a moment. But the period of the standard y equals tan x graph, which is what we're looking at here, the period of that is pi. Okay, the distance between the two asymptotes. So that's y equals tan x. There's no amplitude for tan graphs because they're not wave type graphs, so there's no amplitude. The period, as I just mentioned, is the horizontal distance between the asymptotes. Wow, complicated formula here for the domain. It means that it's defined for all real numbers here, except for all values. If we x values, if we substitute values for k into here, one by one. Oops, sorry. If we substitute values of k in there one by one, if k was 0, x would be pi on 2. If k is 1, x is 3 pi on 2. K is 2, x is 5 pi on 2. So in other words, it's defined, if we go back to the graph, it's defined for all the real numbers except for these values here. Pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2. Now it's hard to write out all those values. That's why this formula comes in handy. Okay, and that formula covers all those values, positive and negative. And it says that k is all the integers, positive and negative. Period, as we said, is pi over n. Now what is n? If the graph is in the form y equals tan nx, okay, the period is pi over the coefficient of x. Which leads us now to some other graphs, which this one here is y equals 2 tan x. Okay, it's a coefficient of 2 there. Now if I magnify this a lot, okay, you can see what is happening here with the graph. Okay, obviously it's almost straightening out. In fact, when the coefficient there is quite large in front of the tan x, They can almost look like straight lines. But we've got a dilation here. If we look at our original graph, which is the blue one, if we take that point there, okay, then the point on the graph, green graph, which is y equals 2 tan x, that same point is now there. So we've got a dilation by a factor of 2 from the x-axis. See how that first point has been taken twice as far away. You can see that there. Oops. See that there and there again. Same thing. So here we can say, take it back to normal size, we could say in this case that the graph is dilated by a factor of 2 from the x-axis. Here's y equals tan 3x. This time we've got dilation by a factor of 3. Once again, if we look close up here, you can see if we look at that point there, it's now up here at 3. It's been taken 3 times further away from the x-axis. Dilated by a factor of 3 from the x-axis. It's y equals 3 tan x. See there, the purple graph, it's starting to, almost look like a straight line. It's got that slight curve. The bigger the coefficient there, the more it straightens the shape of the graph out. Okay, what's this next one? Alright. This is now the graph of, and I didn't write this down, but it's y equals tan 2x. Okay, this time the coefficient has gone in front of the x. Mentioned before that the formula for period equals pi over n. Pi over n. So if we look here, our value of n, okay, the number in front of the x is 2. So the period equals pi on 2. That's tricky to draw now because typically these graphs, if they're not moved left or right or up or down, these graphs will pass through the origin. You can see that does. So if we've got a period of pi on 2, to get our first asymptotes we really need to halve that, because half the period will be there, half the period will be there. So when you're drawing a graph that's got a period of pi on 2, you halve it and go that distance one way and that distance the other. So you can see at my asymptotes here are at pi on 4, neg pi on 4. But the distance between the asymptotes, which is the period, is pi on 2. Because neg pi on 4 to pi on 4, that distance there is pi on 2. So that's tan 2x. What about dilations there? Well, I've got the two graphs now side by side. I've got tan 2x, and which is this one here, just to identify it, and I've got tan x. So that one's tan x, and this one is tan 2x. There we go. Now if we look at our dilations here, you can see that if I take this point here, on the original graph, it's been taken halfway into the y-axis. So it's actually been dilated by a factor of a half from the y-axis. It's going halfway in from where it is to that y-axis. So let's write that out. Tan 2x, dilation by a factor of a half from y-axis. Now obviously if that was tan 3 on x, sorry, tan 3x, that would be a dilation of a third from the y-axis. If it was tan a half x, would be a dilation by 2 from the y-axis. So it's a dilation if we put our equation in the form of tan nx, our dilation is by a factor of 1 over n from y-axis. Okay, Okay, so that's a little handy thing to know. Okay, next graph. Here we've got, you might notice it's going the other way. Okay, instead of sloping that way, whoops, keep forgetting to change pens here. Instead of sloping that way, it's sloping the opposite way. So this one is y equals neg tan x reflected in the x-axis. This one here, this one's been translated a certain number of places to the left. So if I magnify a bit here, you'll be able to see that. In fact, here it is originally, the purple graph, and here it is now. How far has it been moved? It's been moved to negative pi on 4. So all these points on the graph, have been shifted pi on 4 to the left, whichever way you look. So this will be the graph, and remember our transformations before, horizontal transformations. This will be the graph of y equals tan x plus pi on 4. Because a plus there takes our graph to the left. So to the left pi on 4 places. Next question. We've got y equals 6 minus a half tan x on 3. State the period and transformations. Let's start with the period here. In fact, before I do that, I might just I'll change pen colour as well, just to make it look a bit different. I might just write this out in a different way. So we're going to change it to this. Alright. What's the period? Okay, so the period, remember, for tan graphs, different for sine and cosine, is pi over n. What's our n? Well, if we've got x on 3, that's the same as 1/3 x. Okay, so the coefficient is 1 on 3. So our period will be pi on 1/3, which is the same as pi multiplied by 3 on 1 equals 3 pi. That would be our period here. What else have we got? I'll just copy this over to the next slide. Okay, so we've got a negative a half there. So two things are happening there. We've got a reflection in the x-axis. We've got a dilation by a factor of a half from the x-axis. Because we've got 1/3 x there, our dilation, there'll be another dilation here, there'll be a dilation by a factor of, now, as I said, that coefficient there of x there is 1/3. So this dilation is 1 over 1/3. So that's going to be a factor of 3. Whoops. 3 from the y-axis. And finally, we've got a plus 6 there. So there's going to be, the graph will move up 6 places. Okay, so there's our transformations there. Last question I want to show you is this one here. State the period and sketch the graph of y equals negative tan 2 outside of x minus pi on 4 plus 1. And we're doing that between the parameters here of 0 to pi. So it's probably best to take this in steps. The first thing, I mean, you can do this in many steps as you want, but you can start by drawing y equals negative tan x, then negative tan, negative tan 2x, then negative tan 2 outside of x minus pi on 4, and then finally negative tan 2 x minus pi on 4 plus 1. If you take it one step at a time and make the correct transformations, in fact, in hindsight, you're probably better off starting with that one there. Okay, it's probably a waste of time to do tan x. And that's what I've done here. If you look at the next slide here, I've started with graph of y equals negative tan 2x. And it's got a period there of, so we've got our asymptotes of pi on 4 and 3 pi on 4. Our period there, the distance between our asymptotes, is from there to there, that's pi on 2, so that's our period. So that's a place to start with just that graph there. Okay. Now, of course, we're not using any of this space over here really. Okay, but it was a bit hard to limit it on the app that I was using, so we've got the whole graph, but we'll fix that up at the end. So that's first of all is a graph of y equals negative tan 2x, sloping that way, and it's got a period of pi on 2. Why has it got a period of pi on 2? Because period equals pi on n. Our n value is 2. Alright, now what I've done is I've drawn a graph here of y equals negative tan 2 outside of x minus pi on 4. So I've shifted the graph pi on 4 places to the left. Sorry, start again. To the right. So the original graph there is the orange one. The graph that we want now is the black one. Okay, so you can see there, pi on 4 places to the right, the orange to the black each time. Moving that across. So I've made that transformation, and now my graph is at that stage there. But remembering, my original graph that I had to draw had that plus 1 there. Okay, so plus 1 there. So we now have to take the whole graph up one place. And that's what I've done here. Okay, so now I've moved the graph across pi on 4 places and moved it up one place. Okay, so if you compare it with the graph we had before, okay, that point there, for example, has been moved up 1 unit to there. That point there has been moved up 1 unit to there, to there. So I'm taking this black graph from the previous slide and moving all the points up 1, not just the points I'm referring to there, but all points up 1 unit. So that point there, we go up to there, for example, and so on, which gives me this graph here, having moved your graph across and up 1. Okay, so that's a bit of an introduction to trig graphs. Hope that is useful for you.